Alrighty, so I thought we'd have a little look at a maximum power point tracker. And for this I've decided to do it in MATLAB Simulink, and I thought I'd do it with Simscape as well, although you could do this without Simscape quite easily if you needed to. I don't really want to concentrate too much on how the boost converter works. You can find that on the internet if you need it, or you can find it in books like Power Electronics by Mohan, which was published in 2003, I think. It has a black cover. It's undergraduate text on switching circuits, effectively. Anything like that would be fine. It's used sometimes in solar panel arrays, and you can use it in wind turbines and any situation where you want to follow a maxima, oftentimes to match the load to the source. So in other words, it's a thing which makes the boost converter operate optimally as an impedance transformer. And in the case that we've got in front of us, I presuppose a brushed DC machine, just because it's simple, and it's got a certain output resistance, and I think I made it 3 ohms, which is not implausible, perhaps a little bit high, but it doesn't really matter, it's just an example. And we're looking at the input and the voltage and the input current, and these are coming from the Thevenin source. And then we've got a regular boost converter, which is the inductor, the diode, the capacitor and the switch. We're monitoring the switch current and the diode current because it's traditional in these sort of circuits that you have a little look at those waveforms and you do your energy transfer calculations and that sort of thing. As for the driver circuit, I've just got a controlled source and a gate resistance, and that in combination with the gate to all other electrode capacitances will decide the rise time and the switch on of the MOSFET. And I've selected RG, I think it's 100 ohms. Yes. Just so that we don't get too much shoot through in the waveforms up here, so they look like a textbook. Of course, it's easy to make things look like a textbook in the simulator, not quite so easy on the bench. If you're using Simscape, you've got to have a solver configuration block, and I don't think I did anything to this except drop it down. There's nothing magic happening there. And the solver itself, when it loads, it's just the standard. I didn't change anything here either, it just runs. I like simulations like that. If you have to start tinkering with the solver, you need to think about why you have to start tinkering with the solver. It's better if some things cannot run with the standard settings, and that's fine, but you have to have reasons for tinkering rather than just fiddling until it works, which is not a very good approach. So a variable time step solver, and I let it make all its decisions it wants to. Other thing we can have a look at is the output current and voltage, and for the load I've got an inductive component and a resistive component. I think the resistive component is probably 10 ohms, and the inductance is a millihenry. The switching frequency for this setup is a kilohertz, which is rather low. You'd certainly be able to hear it, especially the wound components will have some vibrations in them due to the change in flux density. Same as a transformer in the electrical power system hums when you're near it. Or you can hear it humming when you're near it. It hums whether you're near or not, as long as it's got some current in it. So you wouldn't usually choose to run at a kilohertz, but it's just an example for the MPPT really, not so much for the converter. The thing you've got to think about with the boost converter is you can only increase the voltage from the input to the output. So, or you are supposed to operate it like that. Consequently, we ought to be expecting the impedance of this LR combination to be greater than the impedance of this machine output resistance. If it's not, we ought to choose a different kind of converter. But since this is an example, I have purposely made these the right size. If we wanted to be able to have only down conversion, buck would be a reasonable choice, provided you don't want galvanic isolation. If you do, then you might choose a forward converter. If you want the galvanic isolation and you want boost arrangement, you could either modify a boost converter, try a flyback converter, or you can use a forward converter for that as well. And if you want, you don't care about isolation, but you do want gain and I would call it attenuation, I suppose. You can run buck boost, which is just a chuck converter. Plenty of other options as well. You can look those up if you want. So I've got a block here, which is just two converters from the Simscape united lines to the Simulink lines, and I've got another set here, and this is also taking the mean. Oh no, it's not, sorry, I got rid of the mean. It used to take the mean, but then I changed it. It multiplies the input voltage and input current and the output voltage and output current together, and then it divides them, multiplies by 100 to get the efficiency. This is, as we'll see in a minute, not a very bulletproof method. It presumes that there is no significant stored energy in the system. But there is stored energy in the system, especially under transient conditions, when it's starting up, or when you step the load or something like that. You can get some unusual answers. But from a steady state perspective, when the energy in per cycle and the energy out per cycle are reasonably constant, it works well enough. If you wanted something a bit better, you could do it on integrated energy transferred. It would be a slightly better way. The controller is looking at the input voltage and the input current, so it's reading these two. And then we do some control stuff here. And the outcome of that control is a duty cycle. So 0 to 1, or 0 to 100% if you prefer, but it's 0 to 1. And this is a regular Simulink P&O generator for a single switch converter, multiplied by 10 because this is a 0 to 1 output here, and I want to run the MOSFET. And 10 volts is easy enough to switch on a vertical MOSFET. Of course, it's still not really a voltage, it's just a number. It only becomes a voltage here. I know it's volts. Then we convert into Simscape, and then we run the controlled source. So we can have a look at the duty, and we can have a look at the... So this is a number between 0 and 1, and this is a switching waveform, which is 0 when it's a minima, 10 when it's maxima, and the on to off time is proportional to the value of D. So the usual setup, nothing odd there. And I just got a big scope so I can look at the efficiency and the currents and voltages and that sort of thing. So if I was to run this now, it shouldn't take too long to solve, it's quite simple. If I ran at higher switching frequency for the purposes of the example, and I wanted to simulate over the same amount of time, which is a second, it would take a lot longer to simulate. So that's my other excuse. We'll also have a little look at the per cycle waveforms as well. So just crunching the numbers, and the old fan on the computer is... oh, that may have been loud. So we have a little look at the duty first and see if the controller's doing stuff. It is. I started the duty just above 0, and it can't quite reach 100, or 1 rather, because I've got something in the controller that stops it. If you allow the duty to go all the way to 1 with the boost converter, the efficiency falls very badly because there is no time available for the inductor to dump its energy through the diode and into the capacitor, because the switch is always on. So you wouldn't really want to run too close to 100% duty. But you can see here the duty is ramping up, and we get to about 55% or so, maybe a little bit less. And there is this oscillation in the... right, it doesn't reach a steady state. But because the controller is perturb and observe, which is the most trivial method, you're always going to get this sort of rocking back and forward about the optimum point. And we can have a look at the duty there. It's pretty small, and the duty here is about half, which is good because that's about half, so that looks believable. And if we go and have a look at the characteristics, we can see that there's an efficiency greater than 100% there, which is obviously not true. I wish it was, I could just retire. The reason for that is if we look at the powers, you can see there's lots of energy comes in this first little time period here. Let me zoom in. Yes, loss of energy entering the system here, and no energy leaving, so plenty of energy stored in the system at this time. Energy not coming in so much now, but energy leaving. So because this calculation of efficiency is based effectively at every instant in time, we are getting something for nothing at this instant, which is why we're above 100. If we did an integrated energy approach, that wouldn't be wrong, but when we look at steady state, where they're not changing very much, the input and output powers, actually, this calculation is good enough. So, what's happening? Well, we've got the output voltage is rising to a maximum, more or less. There's a little bit of ripple, and I suspect the tops of the ripple are probably just about equaling the top of that bit there. We might even be able to zoom in on that. Yeah, roughly speaking, that's about the tops of all those and the top of that bit there, just about. There's some ripple, and you could, if you wished, have less ripple, and the way you do that is make that cap a bit bigger or increase your switching frequency. But as I said, I don't really want to deal with a boost converter. You can find the equations for their design online. Output current is about 2, output voltage about 20, so about 40 watts. Yep, that's believable. Input power looks like it's about 46, 47. Input voltage is 11. I'll call it 10 for the sake of argument, so half of the output voltage, and the input current is 4, which is twice 2, so yeah, it's all very believable. And of course, as the input current goes up, the input voltage will drop. When I say input current and voltage, I'm thinking about just here, because this output resistance of the machine is part of the source. I don't count this as part of the converter, so this is the voltage I care about, which is why I've got the source there. So it looks very much as though what's happening is we are adjusting the energy drawn from this source until it's a maximum per cycle. And another way of thinking about that is to say, if I drew a line here on my circuit and I looked at the energy flow to the right of this input voltage source, and I drew a line here and looked at the energy flow to the right of that imaginary line, I could, if I wanted to, develop an effective resistance looking into the output of the converter, looking into the cap and the diode, and I could develop an effective resistance looking into the inductor and the switch and everything else. And you can't really call them small signal resistances because the signals we're dealing with aren't small. We've got switching waveforms, and this large amount of the characteristics of the semiconductor device are being swept when we switch from off to on and on to off. But you can, over the course of a couple of cycles, come up with an idea as to what that resistance would be. You can't say at every instant in time it's such and such, but you can say an aggregated resistance is this much. And if your MPPT is working, you ought to find that the resistance looking into the input of the converter equals the output resistance of your source, and the resistance looking into the output of the converter equals the impedance of your load. This could be impedance as well if I put some inductance or whatever in there. And in that way, effectively, you've got a semiconductor circuit which is doing the job of an impedance transformer. And if you think back as far as you can to the earliest electrical network sort of stuff, then you might remember that if you want to get the maximum power you can out of a Thevenin source, you've got to put a resistance across there which is equal to the Thevenin resistance, and then the voltage will be shared half each, and the current will be a maximum, and so forth. And that will give you the maximum power transferred. So that's what we ought to expect to happen, and the whole thing looks like a big DC to DC transformer. If we look at the algorithm itself, I've got a few extra bits in here I've labelled it so you can press pause if you want to think about it a bit. We've got the input current and the input voltage. So these are taken from here, and they are in turn taken from here. And we multiply the voltage and the current together to get the input power. And then we take the last input power. So this is the input power in the last time step of the simulation. Because it's a discrete time simulation, I know that if you look in the solver it says variable step, but the fact is there are times at which it's doing the calculations, and there are times between those times. So in that sense it is discrete. The fact that the amount of time it takes in each step changes according to how much the equations are non-linear or unwilling to come to solution, to a consistent, self-consistent solution, is neither here nor there. The fact is there are steps, so we can do the whole thing digitally. But if you're doing this in a, I don't know, Cortex M3 or something, you would also be in a digital system by this point anyway. And in fact the zero order holds here sort of, I wouldn't say replicate, that's being a bit nice, are the most primitive expression of what an ADC does that you might want to put into a simulation. This is not an ideal setup we've got here, it's just an example. One of the major problems with it, in fact, is it's quite difficult to, well, not difficult, but it's the stability of the feedback loop that we're creating is deeply bound up with your sampling times and how long it takes you to do your calculations. And what you'd really like to be able to do is do all your calculations and then tune your feedback loop using some separate parameters. Or to do some calculations that tell you how to tune your feedback loop using the parameters you have available. And in this case, you would need to do that working out. The perturb and observe is usually so simple that more or less any numbers you throw at it will probably go. But that isn't an approved design method. So we have the power in the current step and the power in the last step, and we subtract them. So we get the change in power as a function of time, and then we look at the sign of that to know which way it's heading. And we do the same for the voltage. We could at this point find power minima, and if we did, that would be troublesome because you could have your controller driving towards a power minima, and the power minimum will be no duty, no power flow, nothing happening. Of course, that's not very desirable because you want the maximum power point. So we can look at the maximum voltage as well, because across the input we ought to find a maximum or a minimum voltage which is related to the maximum minimum power. So we do the same thing with the voltage. We have the input voltage and the input voltage at the last time step. And of course these only change according to the zero order hold. So I will make the zero order hold sample times longer than the switching frequency. If you don't do that, there is a very good chance of instability. Exactly how long you choose to make it will go quite a long way into determining your loop dynamics. And of course you'd really like to be able to design your loop dynamics not separately, but you'd like to have some more control than just your sampling rate. And then we take the sine of the rate of change of the voltage, and we multiply these together. So we've got either a 1 or a minus 1 here, and a 1 or a minus 1 here. And you multiply them out, and there are four things that could happen. You have a positive rate of change sine of power and of voltage, and that leads you to a positive answer here. Or power is positive, voltage negative, you'll get a minus. Negative power, positive voltage, you'll still get a minus. And negative power, negative voltage, you'll get a plus. So we take the sine of the product of the sines of the derivatives, and that is proportional to the direction in which we should step our duty. So if we find that the duty needs to go up or down, this is what that's telling us according to the minimum or maximum we're trying to head for. And it just so happens that for this particular case and this particular inverter structure, the boost converter structure, there is a minus sign missing. So I've cheated and stuck a minus sign in rather than rewrite this lot. It should be possible though. You would invert one or both of these, but I didn't bother to work it out. Once I realised my error, I just popped this in. It solved the problem neatly. Then you will set up your duty step size. So duty will vary from 0 to 1 in this case, and for every time that the zeroed holds pass through one sample set, which is, I can't remember, 10 milliseconds in this case. So I've got 10 switching cycles before these register a new set of values. So every 10 milliseconds we'll update the duty. Even if the duty is exactly what we'd like it to be, perfect in other words, it will still change. And that's why you get this oscillations. You will always get the converter, the duty cycle is changing each time the controller runs. Now, you might say, well, ideally I'd like it to find the point, the sweet spot, and to sit there. And you would, but the perturb and observe simplicity leads to some downsides, and one of the downsides is it will always oscillate back and forth about the optimum point. So this is the step size we'll take, and if you make this bigger, of course you'll take bigger steps, and your in control system terms, your phase margin in your control loop will be lower because your gain around the loop's bigger, and that obviously leads to a faster response time but the greater chance of instability. And if you make this small, you will have a slower response time but the likelihood of more stability. So I picked this and ran the simulation until it looked alright, which is not the way that you do control loop design. But if you want to know, I'm sure there are some open access journal papers that have various mechanisms for tuning your MPPT perturb and observe controllers. So we multiply the direction of the step by the size of the step, and that gets us the step size and direction, and then a discrete integrator. In other words, it adds up all of these from the past so that you end up in a situation where you're heading in the direction of the optimum. In other words, it's just an integrator. If, of course, this changes, then this becomes effectively a subtraction from the previous value, or rather, this subtraction out a full set of values such that it goes up and down, oscillates about that point. At the very end, I've just got some saturation that allows the duty not to exceed, or to exceed a low value of 0.01, because I don't want the converter to switch off and stay off, even though it shouldn't. It could happen, I should think. And I don't want the converter to run up to the point where the switch is always on. Power in the switch would be very large and the efficiency falls down dead. And out of that comes our duty. So that's how the controller works. And that generates the duty, which gives us a PWM according to the regular Simulink block. So if we take a look, did we see this? I think we did. Yes, that's one example. You can see this back and forward. And that's why these steps are the length they are in time without any change. That's because that's the length of the zeroed hold, so 10 milliseconds. So obviously if I was to change the length of the zeroed hold, it would have more changes here. You don't really want to change too much because you need a little bit of time for everything to settle out. Or rather, you need stability in your feedback loop. We take a quick look at the waveforms that you'll find in textbooks. We have a switch current is yellow and diode current is blue, and you could integrate the area under here and get the energy if you wanted to. Or rather, you get the charge and then you could use the voltage and then you could get the energy. And you can see that this is what you'd expect. We have the charging up of the inductance, or rather the increasing magnetic flux density around the inductor, and then we have the switch switching off and the inductor magnetic field starting to collapse and the energy being transformed into a current driven by the back EMF which is produced, and that switches on the diode and the diode conducts and we have the current in the diode, and then the cycle repeats over and over and over. We want to have a look down here. Here we can see very short charging up of inductance, magnetic field, very long. You can even see a slight exponential there, I think, if I was to zoom in a bit. It looks pretty straight, but I bet you if we got a ruler up against the screen, that's slightly exponential. Well, it is slightly exponential. Whether you can see it or not is perhaps the question. And there we are. So that's the simplest possible, one of the simplest possible strategies for a maximum power point tracker. Email me if you've got any questions.